In this video, we're going to take a look at the mole. Specifically, we're going to take a look at and see what exactly is the mole, also referred to as Avogadro's number, and then we'll look to see how we can use Avogadro's number in calculations to help us determine the number of moles of a substance or the number of particles we have in a substance. But before we get talking about what a mole is, let's review what a conversion factor is. Earlier this year, we spent some time talking about conversion factors when we went through dimensional analysis. Take a moment to think about what a conversion factor is and some examples. A conversion factor is a way for us to convert from one unit to a different unit by using a value, also called a conversion factor. An example would be 60 seconds in 1 minute. 60 seconds in 1 minute allows us to convert between the units of minutes and seconds. Another example would be 12 inches in 1 foot. This conversion factor allows us to convert between inches and feet. The mole, then, is simply a conversion factor that allows us to convert from moles to the number of particles present in a sample. We use the term mole to indicate very large quantities of substances because when we talk about atoms and molecules and ions, we're referring to very small things. A mole, then, is equal to 6.02 times 10 to the power of 23 particles. This number can be thought of like you would the word dozen. Dozen simply means 12. So if I told you there was a dozen donuts sitting in the classroom, you would know that I was referring to 12 donuts. If I told you there were a dozen elephants sitting in the classroom, you would be thinking in your mind 12 elephants sitting in here. The same is also true with the word pair. A pair simply means 2. So a pair of textbooks tells you that there are 2 textbooks. Or a pair of calculators tells you that there are 2 calculators. The same is true with the word mole. A mole simply tells you that there are 6.02 times 10 to the power of 23 of that thing. There are other words in the English language that also mean a quantity. Can you think of any of them? Some that I came up with were a baker's dozen, meaning 13, the word score, as in 4 and 7 years ago, meaning 20 for the word score, and gross, which is 12 dozen, or in other words, 144. There are definitely others beyond these ones. Going back to some that we're more familiar with, though, like pair and dozen, we could go through and complete this chart. A pair of pennies simply tells us there are 2 pennies present. Same with a dozen pennies. Dozen pennies tells us there are 12 pennies. So when I use the word a mole of pennies, I would be referring to the number of 6.02 times 10 to the power of 23 pennies. And I can use those same words, a pair being 2 and a dozen being 12 in reference to a donuts. And a mole of donuts then would be 6.02 times 10 to the power of 23. Now, when we're talking about pennies and donuts, it makes sense to talk about pairs and dozens. But when it comes to carbon atoms, a pair of carbon atoms, 2 carbon atoms, doesn't really make a lot of sense because atoms are pretty small. Same for a dozen. A dozen atoms, even though it's 12, it's more, is still a very, very small number of atoms. But it makes sense for us to talk about a mole of atoms. In other words, 6.02 times 10 to the power of 23. So where exactly does a mole come from? Well, a mole is the amount of a substance that is present in exactly 12 grams of carbon-12. And that is where Avogadro's number comes into play at. Now, in terms of this number, 6.02 times 10 to the power of 23, this is a very, very large number. To try to put this number into perspective, we're going to take a look at some different stats. And so you can work your way through these and take as much time as you want. But ultimately, the idea here is that a mole is a very, very large number. If we look at something like stars in our galaxy or distance to the sun in inches, even our national debt or the cells in your body, these numbers don't even come close to how big a mole is. A mole contains a lot of substance, a lot of things. Here are some other examples. If we were to have a mole of, say, marshmallows or rice grains or baseballs, just how much is that? So you can take a minute, read through those. And here, if we actually had that mole of pennies that we were referring to, this is what you would get. Sounds great at the beginning, but maybe not so wonderful by the time you get to the end. So now that we understand that a mole is a very, very, very large amount, think about this question. If we have a mole of water molecules, how many molecules is that? Well, remember, molecules are very, very small, much smaller than even things like rice grains. And so a mole of water molecules is just 18 milliliters. Now this is a much practical amount much more practical amount for us to talk about. Doesn't make sense to talk about a mole of rice grains because that's such a huge quantity. But when we talk about something that is so small, smaller than a rice grain, it makes sense to use a mole. And so this is why chemists use the number. So now let's take a look at how we would use a mole in calculations. We're going to go back to our old familiar example of a dozen, just so that we have some practice using this. All right. So starting off, if I told you that you had 10.5 dozen of donuts, how many donuts would that be? Well, the first thing we have to do in every calculation is figure out what our given is and what it is that we want. We can see in our problem that we were given that we have 10.5 dozen donuts, and we know that in the end we're trying to figure out how many donuts we have. So in every dimensional analysis problem, we always start with a given, put it over 1, multiply by conversion factors to get to our final answer. So I'm going to start by taking my 10.5 dozen donuts, and I'm going to put it over 1. And then I set up my conversion factor. So I know I'm going to put dozen in the bottom, and I'm going to put just donuts up top. And I know that every 1 dozen contains 12 donuts. So I plug in my values, and then I check. Units cancel, and I am left with donuts, how many or the value that I wanted. So at this point, I can grab my calculator, do my multiplication, and we come up with 126 donuts. Now if we take a moment, we can't forget about significant figures. So going back, 10.5 is a measurement, and so we know this has 3 sig figs associated with it. Coming over here, we know that 12 donuts in a dozen is an infinite because it's a count, and that gives us 126 donuts. And so smallest number here would be 3, so my final answer should have 3 significant figures, which we see that we do. Double checking, does it make sense that we would have 126 donuts in 10.5 dozen? Yes, it does. So my answer also checks out. So let's move now to taking a look at how we would do this type of a problem when we were faced with moles instead of dozen. So still talking about donuts, though hopefully we recognize this isn't going to be a feasible option. But we see we want to figure out how many donuts are there and 10.5 moles of donuts. So again, taking a look, we see we start with moles of donuts, that was what we're given, and we want to ultimately figure out how many donuts we have. So beginning with our 10.5, we're going to place 10.5 moles of donuts, and moles is abbreviated with an MOL. I know it's not much of an abbreviation. And we take our given, we put it over 1, and then we multiply by our conversion factor. So we're going to place moles in the denominator, and then we're going to place our donuts in the numerator. And remember, 1 mole is 6.02 times 10 to the power of 23 things, whatever those things happen to be. So the number 1 goes with moles, and the number 6.02 times 10 to the power of 23 goes with donuts. All right, so now I take a look, my units cancel, leaving me with units that I want, so this is good. So now I can go ahead and grab my calculator and multiply this through. Make sure that you're being careful to use correctly entering your scientific notation into your calculator. We should end up with a number then of 6.321 times 10 to the power of 24 donuts. And once more, before we can be done, we have to check sig figs. 10.5 has 3 significant figures to it. And Avogadro's number, even though this is a count, this is coming from a measurement. So this has 3 significant figures as well. The 6, the 0, and the 2 are significant. So taking a look, my smallest number of sig figs would be 3, leaving me with just 3 here. And do I round the 2 up? No, I don't. So my final answer would be 6.32 times 10 to the power of 24 donuts. All right. Working our way through a chemistry example. This time we're going to change up the question a little bit. This time we want to know how many moles of copper atoms would be present in 3.62 times 10 to the power of 22 atoms. So once more, taking a look, here is our given, our number of atoms of copper, and we're looking for moles of copper. So I start by placing my given, 3.62 times 10 to the power of 22 atoms of copper over 1. And then I set up my conversion factor. I take the units that I want and they go into the denominator. And I take the units that I have go into the denominator, and the units that I want, moles of copper, go into the numerator. And then I plug in my numbers. 1 goes with moles, and 6.02 times 10 to the power of 23 goes with my atoms. Double checking units, we see atoms of copper cancels. I'm left with the units that I want, which is moles of copper. So now I'm ready to grab my calculator, and dividing these two out, gets me 0.0601329 moles of copper. But once more, we have to check significant figures. Here we should have 3 sig figs. Down here we have 3 sig figs, giving me 3 as my smallest number. Leading zeros do not count, so we have 1, 2, and 3. Because this is less than 5, I don't round up, and my final answer would be 0.0601 moles of copper. And moving to our last example, we're going to take a look and figure out how many molecules of carbon dioxide we have. Take a moment to try to complete this one on your own, and then unpause your video and we'll go through it together. Alright, so taking a look here, we should recognize that we are given a 12.82 moles of carbon dioxide, and we want to find molecules of CO2. So starting off with our 12.82 moles of CO2, put our given over 1, and then we multiply by our conversion factor. Units that we have, moles, goes in the denominator. Units that we want, molecules, goes in the numerator. 1 goes with moles, and 6.02 times 10 to the power of 23 goes with molecules. Double checking units, moles cancels, leaving us with molecules, which is what we want. So now we can grab our calculator, and we end up with paying attention to significant figures. We have 4 here and 3 here, so my final answer can only have 3. We should get 7.72 times 10 to the power of 24 molecules of CO2 present in that 12.82 mole sample.